Please give me some minutes. I want to load the PowerPoint slide from my presentation, and I think you can also do that from your end, so that when it's time for your presentation, we already have it on the stage.
So it's not like us sharing screen. We have to first like upload it before we can present.
Yes, yes, sure. You have to first upload it.
Okay, I see.
It's still loading. Great. I hope you can see that from our videos end.
Yes, we can.
Oh, that's great. That's great. Yeah. So I think we are set now to start the webinar. Yeah. Hi everyone. It's good to have you tune in to this webinar today. It's a memorable day for every one of us speaking today at this webinar. Personally, this is my first ever webinar that I will be hosting at the same time I will be speaking. And while I'm not sure that's the same for Mr. Tomiwa, I want to believe it's the same for Dr. Asen Ayola, Dr. Ayodeji. Before I go into my presentation, I would like just to say a few things. Number one, I would like to apologize for the unavoidable absence of Mr. Ayomipo Sifalade, who is a PhD candidate at the University of Memphis, USA. He is unavoidably absent because he has some deadlines to meet with in his academic study, and I take responsibility for that, for his absence. And so you wouldn't have him making his presentation here today. So you'll be having presentation from myself, from from Mr. Tomiwa Akambi and Dr. Ayodeji Asen Ayola. Once again, you are welcome this evening to this webinar, and this webinar is brought to you by Tosinju Consulting Limited. Tosinju Consulting Limited, together with the support of the speakers you are seeing right now on your screen, and the topic of today's webinar is the fundamentals of magnetic data interpretation. And what actually brought about this idea is because there have been so many people reaching out, not just to only me, but also to some of the people you are seeing here, people reaching us out that need assistance in getting to know how they can interpret their magnetic data. It is one thing for you to have your magnetic data acquired. It's another thing to have your magnetic data processed. And it's another thing to have your magnetic data being interpreted, and not just interpreting it anyhow, but appropriately interpreted to suit the purpose for which you have acquired and processed the magnetic data. So this is an insightful webinar, and I believe that it will not be a waste of your time. Please take your seat wherever you are and pay rapt attention to us as we'll be speaking from the volume of experience that we have garnered over the years working around the magnetic method of geophysical prospecting. My name is Tosin Oyeniyi. I am the founder of Tosin Geo Consulting Limited, and I'm the one hosting this event. At the same time, I will also be speaking today. Right on your screen now is the PowerPoint presentation, presentation that I have for you this evening, and the aspect of the webinar that I will be handling this evening, uh, this afternoon rather. Sorry, because I know that there will be people joining us from different time zones of the world. And permit me to use the word if I have to know, because right now in Nigeria we are in afternoon, so I don't know what time of the day it is at your end. So the aspect of the webinar that I will be handling this afternoon is the global perspective of magnetic data interpretation. But before I go into that, I have few things for you. The first thing is I would like to just give you some overview concerning El Tosin Geo Consulting Limited, and then concerning Magradel, the conceptualized idea that through which we are bringing this webinar to you today. El Tosin Geo Consulting Limited is a geotechnological and geophysical consulting company focused on leveraging digital technologies to provide solutions at the nexus of energy, minerals, and environmental assets towards achieving digital health transformation and development. I believe that is very clearly enough, and we shouldn't take much of our time on that. And then the next slide I have is what is Magradel, because this webinar is one of the series under the concept that we have put forth, and that concept is Magradel. And as you are seeing on your screen right now, Magradel is an acronym of magnetic, gravity, radiometric, and electromagnetic methods. And it is both a tutorial-based and mentorship-based initiative of El Tosin Geo Consulting Limited. It leverages video technology to provide educative, insightful, and relatable content on geophysical methods, including magnetic, gravity, radiometric, and electromagnetic methods. This initiative covers their theory, data gathering, processing, and interpretation using digital technologies such as software, as well as their application in energy exploration, mineral exploration, and environmental asset assessment. Actually, there is a YouTube channel that has been created for this initiative. I'm sorry that I forgot to add that to this slide, but if you are on LinkedIn right now, you can go through the event and you'll be able to see the link. In the details of the event, you'll be able to see the link to the YouTube channel that have been created for the initiative. And before I move to the global perspective of magnetic data processing again, there is before you the Geophysical Sustainability Atlas. This Geophysical Sustainability Atlas was extracted from Capello et al. 2021. The work on mapping geophysics to the United Nations Sustainable Development Goals. So they ensure that they redefine geophysics in the context of the United Nations Sustainable Development Goal. And one of these United Nations Sustainable Development Goal, which is Goal 4, is quality education. So Magradel, as an initiative of El Tosin Geo Consulting Limited, is seen as an initiative that is meeting the needs uh, means required by the United Nations Sustainable Goal 4, which are demands for quality education, for quality education. So this is not just an initiative of just a company alone. It's an initiative also that is speaking also to meeting the United Nations Sustainable Development Goal, particularly the United Nations Sustainable Goal 4. Now, I will be starting my presentation now. I want to look at the global perspective of magnetic data interpretation, and so starting on this note, I have a question here in this slide that is there actually a global perspective? I know when many would have seen this and they will be wondering that what do we actually mean by a global perspective? Is there actually a global perspective of magnetic data interpretation? Yes, as will be seen in this presentation, there is a global perspective. However, we need to define what we mean by this global perspective. We also need to define this concept of global that is being used at this time. Global, as you have seen in the first bullet of the slide before you, global in this context refers to considering the variation in the nature, behavior, and measurement of Earth's magnetic field across different magnetic regions of the globe and their implication on magnetic data interpretation. So what this is telling you is that when it comes to the nature, the behavior, and the measurement of Earth's magnetic field, there is a variation across different magnetic regions of the Earth. So there are actually different magnetic regions of the Earth, and the behavior, the nature, the behavior, and the measurement of magnetic data across these different regions are not the same. So if we will actually talk fully holistically concerning the fundamentals of magnetic data interpretation, then we will need to have to look at it from every side of different aspects of the globe, and that is what brings about this global perspective of magnetic data interpretation. And the next bullet is the Earth behaves like a giant magnet. So I will need to the reason why I make a definition of what I mean by global perspective is that we are having people from different parts of the world that will probably be joining this webinar and that will be watching this webinar later. So it is very important that we create a common ground that will be a leverage for every one of us to understand the things that will be discussed later on in the various sessions, in the different sessions of this webinar concerning the fundamentals of magnetic data processing. So it will not be like when we get to certain aspect of the webinar, like the Nigeria perspective of magnetic data interpretation and the challenges of magnetic data interpretation for somebody who is not domiciled in Nigeria, but another country which is not even in the equatorial region. The person will not be looking at some things that will be said in Nigeria perspective of magnetic data interpretation as something strange to the person, because the person might probably have been so acquainted with with the polar region. So hearing concerning the interpretation in the equatorial region might sound strange to the person. So it is very important that we create this common ground that will be able to leverage on to bring everybody together into the perspective of fundamentals of magnetic data interpretation. So back to my second bullet, the Earth behaves like a giant magnet with a magnetic field anomaly around it, which is created by the dynamo effect in the core. It is created by the dynamo effect in the core. So I will take that again. The Earth behaves like a giant magnet with a magnetic field generally accepted to be created by the dynamo effect in its core. So by the lower left hand side, you can see this is the image showing the internal structure of the earth. In the internal structure of the earth, you have from the surface, you have the crust. From the crust, after the crust, you have the mantle, the approximately concentric layer. From the mantle, you have the core of the earth. So within the core of the earth is where there is that dynamo effect that is leading to the generation of magnetic field around the earth, which makes the earth to behave like a giant magnet. We are going through this in establishing the global perspective of magnetic data interpretation, because there's possibility that there are people that do not have geophysical background and do not even have geological background, that are making a transition into from their initial profession into geophysics, into geology. So it is very important that we take these people also into consideration and we make certain points before we go into the global perspective and the relevance of the global perspective to the fundamentals of magnetic data interpretation. Aside from protecting the planet, that bullet three now, aside from protecting the planet's surface and organisms from harmful solar particles, the Earth's magnetic field has been harnessed as the oldest geophysical prospecting method. So there are several geophysical prospecting methods. All these methods are making use of physical principles, principle of physics. They have their operative physical principles by which they are being used in geophysics to explore the subsurface of the earth. And one of these method is the magnetic method of geophysical prospecting. It is actually the oldest geophysical prospecting method, and it is being made clear in this theory that aside that the Earth's magnetic field, it protects the planet surface and organisms from harmful solar particles. So there are particles flying in space. There are particles flying outside of the orbit of the Earth that are trying to find their way into the orbit of the Earth. So, but thanks that we have the Earth electromagnetic field that is able to prevent some of these harmful solar particles from entering into the Earth and hurting the planet surface and the organisms in the Earth. So, magnetic field has been harnessed. Earth's magnetic field has been harnessed as the oldest geophysical prospecting method. And then the fourth bullet you have on your screen, it is very important because if you look at this, your left hand side, you will see that uh, a picture at the top left hand side shows the Earth's magnetic field, and you can see that there's a distinction between the geographic north and south and the magnetic north and south. So this is a simplified picture, is a simplified image that is showing the magnetic field around the earth, and showing also the axis of the earth magnetic field, and showing you that there is an angular difference in the location between the axis of the earth magnetic field and the geographic axis of the earth. And you will also discover that in this image that the if you look at the magnetic flux now, the magnetic field lines, you will see that there is a concentration of this line at the poles, at the poles of the earth, whereas you don't have that at the center of the earth, let's say the equatorial region of the earth. So this is showing us, as I said earlier, that the nature, the behavior, and the measurement, there is a variation across the different regions of the earth, and we need to take this into consideration if we will be able to do a proper justice to the fundamental of magnetic data interpretation. So the fourth bullet now, magnetics is generally more complex due to the nature of Earth's magnetic field, but it is understandable, interpretable, and applicable. So actually, I remember then during my undergraduate study when we were about to start uh, the course on magnetic methods, I had a lot of things from people concerning the magnetic method that is a very complex method. So many people at that time did not really even have interest in the method because of the complexity that is associated with it as a result of the nature of Earth's magnetic field. However, I got to discover later that it is understandable. If you are able to understand it and you are able to think magnetic, you should be able to interpret and be able to apply the method for anything you want to achieve through geophysics. So take note that magnetics is generally more complex due to the nature of Earth's magnetic field, and you will soon see the complexity. Now, the second question: what makes magnetics complex? So you have another picture on at your on my own screen, and it's at the left hand side, and this is more complex than what we saw earlier concerning the Earth magnetic field. And as you can see now, we are seeing that the magnetic north of the Earth is actually the geographic south pole of the Earth, and the magnetic south of the Earth is actually the geographic north pole of the Earth. And we can see clearly that the concentration of the magnetic field strength at the poles, and it is not concentrated at the equator. But before talking so much on this image, I would like to go back to the point I have by the right hand side. What makes magnetic complex? So, as from the last slide, I said it is due to the nature, and this nature impacts the behavior and the measurement also. So, the first bullet you have here under what makes magnetic complex is that it is due to the multipolar patterns of Earth magnetic fields. Take note that I didn't say the polar pattern or the dipolar model. I said the multipolar patterns of Earth magnetic. It is actually multipolar, but because we need to simplify things so that we'll be able to make an meaningful applications of the Earth magnetic field, there is a first approximation of these multipolar patterns of Earth magnetic field to a dipolar model, which is convenient for us to work with. So there it has a multipolar patterns, and the multipolar patterns which are by force as approximation, we have it as as dipolar model, which is convenient for us to work with. So that's first reason why the magnetic as a geophysical processing method is complex. Now, the second thing I want you to know is that the Earth magnetic field is a vector. It is not a scalar quantity, it's a vector. That is, it has both magnitude and direction. It has both magnitude and direction. It has both magnitude and it also has direction. As you can see, even from the magnetic flows, the lines of the magnetic field, you can see there is direction. There's the direction of flow. So it has both magnitude and it also has direction. It has direction. And then also, the variations in Earth magnetic field are erratic. They are erratic and localized. They are erratic and localized. So what do we mean by they are erratic is that sometimes it's difficult for you to have a definitive pattern, a definite pattern that you can predict for the behavior of these variations in the Earth magnetic field. And also, when we mean that it is localized, is that the variations in the magnetic field does not always capture, when you take magnetic measurement, it does not always capture regional effect. It captures mostly the local variation. So it is made up of more of local variation. That's why whoever has practical experience in magnetic data processing, you always discover that when you do your regional residual separation, it is more of the same. It is more of the same like what you have before you do the regional residual separation, because unlike gravity method where you have more of the effect of more of regional effect, in magnetic, the variation is more of local variation, localized variation. And once you have you having more of local variation makes it complex. That's why you have several anomalies represented on your what on your magnetic data. So there are three things I've listed now, and however, these three things they have correlation with the also with the nature of the Earth's magnetic field. And if you understand the nature, in the nature of Earth magnetic field, there are three components of it. Now, in the three components of this nature of Earth magnetic field, you have the main field, you have the main field, you have uh, the main field, you have the external small field, and you have the spatial variations. The spatial variations. So when I talked earlier about the variations in Earth magnetic field, there are time variations and that there are also spatial variation. So variation with time and variation with what with distance with space in space. So the main field is actually that field that is generated from the core of the Earth, core of the Earth, and there is a variation that is also associated with this main field, which is called the circular variation, and that is the variation in the magnitude and direction of this main field. So you can see all these variations that are the variations which that are likely to happen in that magnetic field. It is a vector field and it has multipolar patterns, which we in first approximation we are taking as dipolar model, which is convenient for us. You can see that there is the magnetic method is complex, is complex, is complex. However, having understanding of the interplay of all these will help us to do a proper justice to the interpretation of our magnetic data. So you have the main field, you also have the external field, which are small field. These are time variation in the magnetic field, which are due to external source. The circular variation is an internal source, so internal from the core of the Earth. But the external field, which are this small field, part of this Earth field, they are from external sources outside of the Earth, and these are time variation in the Earth magnetic field. Example of them is diurnal variation and magnetic storms. So those are just the two examples that I want to give for now. There are others examples, and then the third uh, aspect of Earth magnetic field is the spatial variations. This is the variation that corresponds to the geological effect of the upper crust of the Earth. You know, the crust is the outer layer of the Earth. So we are now looking at the upper crust of the Earth because more of our investigation of our geophysical work is more of near surface not surface investigation, and so we are looking at the upper part of the crust, upper part of the crust, and more so more so there is a depth into the earth which are magnetic minerals, they lose their magnetic properties. So that's the Curie temperature, and at the depth at which you are achieve that is the Curie depth. So the magnetic mineral tends to lose their magnetic properties, and as a result of that, we are looking at more. Even though the depth of investigation of magnetic method is to the core of the Earth, but most times for our application, it is more of the upper crust that we take into consideration. So in the spatial variations, another thing in this spatial variation of magnetic in the Earth magnetic field as a result of the geology of the upper part of the crust is that which makes magnetic field magnetic complex is that the magnetism that is measured as this spatial variation in the upper crust of the earth, which is of interest to us in magnetic method of geophysical prospecting. There are two types of magnetism that create these anomalies in the magnetic data of the upper crust. There is the induced magnetization and the remanent magnetization. Even when it comes to remanent magnetization, there are different types of remanent magnetization. So time will not permit to be going into the details of that. So you have the induced magnetization, which is as a result of the magnetic field induced in the magnetic minerals in the rocks in the upper crust of the earth. But there is the remanent magnetization, which is historic magnetization that is preserved in the rocks as a result of the magnetic field that was the nature and the characteristics and the behavior of the magnetic field that was prevalent in the past. So there is the induced magnetization and the remanent magnetization. But what we do most times when we are interpreting magnetic data is that we assume that there is no remanent magnetization, but we focus more on the induced magnetization. However, if for certain study like archaeological study, it is very important you take remanent magnetization into consideration, because it helps most time when in comparison with the induced magnetization. There is a way to go about it that it helps to determine the age of artifacts in archaeological studies. So these are the things that make magnetics complex. So you can see now that even now, as you are seeing in uh, this image on your left hand side, it's on the left hand side of my own screen right now. You can see now that you have the magnetic north, you have the magnetic south, and if you look at the southern magnetic pole, you will discover that you are seeing something like a minus 90 degree there, and at the northern magnetic pole there is 90 degree there. That is pointing to the a particular characteristics of the earth magnetic field, which we refer to as inclination of the magnetic field. So at the poles, the inclination of the magnetic field is 90 degree. At the equator, it is zero degree. Around South Africa, it is around minus 64 degree. Around Germany, it is around 67 degree. And you will discover that, as I said earlier, that the magnetic field is flux is concentrated at the poles. That's why you will discover that the strength of the magnetic field is highest at the pole. That's why you are seeing minus 60,000 nanotesla and also 60,000 nanotesla closer to the pole. Meanwhile, when you come to the equator where the inclination is 0 degree, you are having magnetic intensity, the magnitude of approximately rather, not minus as I said earlier, approximately 30,000. You are looking at 30,000 nanotesla. So actually the magnitude of the magnetic field associated with the spatial variation that we are interested in, which is from the geology of the upper crust of the earth, is not of the order of thousands. It's not actually of the order of thousands. You are having this magnetic field intensity to be order of thousands on this particular figure because uh, there is the addition of the magnetic field from the core of the earth. So, and the magnetic field from the core of the earth is the one that is really bulky in the magnetic data being acquired uh, in the field. So you see now the magnetic field is very complex, and you can see now that the behavior is not the same from the magnetic poles to the magnetic equator. There's a different behavior as a result of the dipolar nature of because of the dipolar nature. You have the pole, there are the two poles, and you have the equator. There is an equator of that magnetic pole, of the equator of the magnetic dipole. So at the equator of the magnetic dipole, the magnetic field strength is not as higher as it is at the pole. And then the inclination there is 0 degree. So all these have effect. They have effect in you on the interpretation of your magnetic data, because this nature, the behavior, and these they are transferred into the measurement, and you need to take them into consideration when you want to interpret your magnetic data. Also, what is the import of this into interpretation? All this I've mentioned concerning the complexity of magnetics. Now, the first thing is concerning the dipolar nature. Now, so due to the dipolar nature of Earth's magnetic field, which behaves differently at the poles. Sorry, I forgot to say this, that if you have any questions as this webinar is in progress, you can drop your comment on LinkedIn. You can drop your questions on LinkedIn in the comment section. And as it is being shown to us here, later on in the webinar, we will attend to every question. Due to the dipolar nature of Earth's magnetic field, which behaves differently at the poles and at the equator of the dipole, as I've explained earlier, the characteristics and interpretation of magnetic anomalies differs at these two locations. It differs at this location. Quickly, I will move to the next slide, and I will come back to this slide to illustrate it. Now, this slide you are seeing now, I have as I have synthetic data here, magnetic data here. So this is the module, the module containing the bodies that were used to generate the synthetic magnetic field. And this is the 3D view. You have first the 3D view, then you have the planar view of these magnetic sources. And the first magnetic data generated, that is the third figure, the third image, is was actually generated for the equator. It was generated for the equator, and the fourth image you are seeing was actually generated for the pole. So for the same body, from the same bodies, and you can see that the response, even though in the texture, the appearance of it, they are similar. However, when it comes to the matter of the amplitude and the amplitude, there is a complete difference. So one is a mirror image of the other, and that is what you are seeing on this. That's what you are seeing on this profile view right now. This is a profile view along the line PP prime taken on the two synthetic magnetic data, the two set of synthetic magnetic data generated at the equator and also at the pole. So you will see that one is the mirror image of the other. So that in the parameters that were used to generate this synthetic magnetic data, actually the body A. So we are looking on the profile, we are looking at body A, B, C, because the profile was taken across bodies A, B, and C. So the body A actually has the highest magnetic highest magnetization. But you will discover that in this third image now, the upper third image, which is generated for these bodies at the equator, where the inclination is 0 degree at the magnetic equator, you will discover that the magnetic field that was generated for this body A, it is low. It is low. It was a low compared to what you have generated for these same bodies at the pole. At the pole, it is high. So which means at the pole, your high is high magnetization. But when you come to the equator, your low at the equator is high magnetization. So for somebody who has been so used to dealing with magnetic data at the pole, and you give such a person the magnetic data at the equator, if the person doesn't have this global perspective of magnetic data interpretation, this global mindset, such a person will just make a false interpretation of the data, assuming that what is actually looking in the equatorial data, magnetic data, is that what I is my magnetization, which is not true. It is not true. At the pole, high magnetic field is high magnetization. But at the equator, your low magnetic field recorded is actually what is actually high magnetization. So you can see now where the importance of this global perspective that we are bringing in this webinar concerning the fundamentals of magnetic data interpretation. So which means anyone from different region can actually relate with us now in whatsoever we will be saying after on, and even if you are given data of different region. So I don't want to belabor the point. I think that illustration, that just one illustration I just made now, has made it clear. Now, back to my import of the complexity now that we've checked into interpretation is that when it comes to the vector quantity also, because Earth magnetic field is a vector quantity with the magnitude of its different component measurable, it is also important not just only to know, as we saw from the effect of dipolar nature, not just that it is important when you want to carry out interpretation to know the magnetic region where your data was acquired, you must also know the type of magnetic data that you want to interpret, because there are different components of Earth magnetic field and they can be measured. Is it the total feed that is measured in that region? Was it horizontal feed? Was it vertical feed? Or what is gradient magnetic data that you are dealing with? Because there is gradiometer that are being used to measure the gradient of earth magnetic field even from the feed. So these are the implication of the vector quantity that the earth magnetic field is. It's not a scalar quantity, it's a vector quantity. And then the effect of the localized variation now, because the variations in Earth's magnetic field are localized, understanding of local geology, topography, and infrastructure will help to discriminate between geological and non-geological related anomalies. Non-geological related anomalies. So these are the import of the global perspective, which we have seen from the lens of the complexity of the Earth magnetic field, which is imported into magnetic method. We have seen that import of it into the interpretation of earth magnetic. The first, you must identify the region, magnetic region where your data is acquired. It will inform your interpretation. At the pole, high magnetic field is high magnetization, but at the equator, low magnetic field is all high magnetization. So when it comes to the kind, you must also know the kind of magnetic data you are dealing with. Is it a total field, horizontal field, vertical field, or gradient magnetic field? And then also, you must also be ready to understand the local geology, the local topography, and infrastructure setting of the area, so that you'll be able to discriminate between magnetic anomalies that are due to geological effect and those that are non-geological related in the magnetic anomalies or magnetic data that is being presented to you. So that is all from my end as far as the global perspective of magnetic data interpretation is concerned in these fundamentals of magnetic data interpretation. Now at this juncture, I will have to hand over to Mr. Tomiwa Akanbi, who is a senior geophysicist at the Nigerian Geological Survey Agency, and he will be taking us through the Nigerian perspective of magnetic data interpretation. So there is none of the speakers here that I've known for less than 5 years. I've known each one of them for nothing less than 5 years. So, and I'm confident that they will deliver excellence to you in this webinar. So, Mr. Tomiwa, over to you. I hope you are still on the webinar.
Can you hear me?
We can hear you.
All right.
It's over to you.
I feel we should have gone through these slides before we started, so that I'm going to know what and what's not to repeat. But it's fine. I like the way you have broken down the global perspective. So basically, I'm going to be talking about the Nigerian perspective of magnetic data interpretation. And
Okay.
I'm going to be basically keen towards the solid mineral aspects, because my specialization is towards solid minerals, not oil and gas. Of course, magnetic data, it has its usefulness to when it comes to the reconnaissance mapping for oil and gas. Or in my own case, I'm just going to be focusing more on the solid minerals. So these are my outlines. We're talking about how to understand and handle magnetic data that is acquired in Nigeria. And I think you also said a lot about that too. And then how to interpret magnetic data for solid mineral exploration. What are the things that you need to consider? What are the factors that you need to put in place before you consider magnetic data to be one of the data sets that you would need to interpret? Because it's not every mineralization that you're looking for that requires magnetic data interpretation. For some, magnetic data is not useful at all. So we need to understand the factors that we need to consider in choosing the methods that will be optimize for whatever mineralization that we are trying to explore. And then we also talked about the importance of integrating other geophysical methods, because it's not every time that you have magnetic data to be a direct method. In some cases, magnetic data can be an indirect method to reduce the zone of search for whatever mineralization that you are looking for. And then after you have drastically reduced the zone of search, you use some other geophysical methods to follow up. And in choosing the method to use to follow up, what are the things I need to consider, and then we'll conclude from there. So basically, magnetic data interpretation plays a very important role in understanding the subsurface geology of Nigeria. Geologists can only make inference based on what they see at the surface, and then sometimes when they do pitting and then take samples to the lab, they interpret, they do their petrography and all of that, but they are still restricted to what they can see at the surface. So in a situation where there are some geology that are not having surface expression, magnetic data sets can be helpful in revealing such within that environment. And considering the country's diverse geological terrain, where you have the basement terrain, you have the sedimentary terrain, you have younger granite and the likes, So magnetic data can help you to differentiate between each one of them on a regional scale, and even sometimes on a local scale. And then just like I mentioned before, magnetic surveys has been used mostly in Nigeria to identify potential mineral deposits, and then to delineate geological structures and characterize the subsurface geology. So here's a typical example of a geological map of an area, and then the total magnetic intensity map of that same area. You can begin to see some similarity between what we have on the geological map and the TMI, regarding the shapes, the places where those lineaments are sort of concentrated, where we're having smooth anomalies, like this place that is reading NLG, that's Lithosin tectonic granite. The granitic intrusion came in, and then there was no major tectonic events afterwards. So you are seeing that on the TMI data on the left, it's looking smooth. And then despite the fact that it's a crystalline terrain, it's looking smooth because it's a late phase intrusion, and then you can see those rounded shapes, proving that they are also intrusives. And then on the southeastern directions, you can see those northeast southwest trending structures. And on the geological map, it has been interpreted to be part of those volcano-sedimentary supercrustal units. So basically, you can see the similarities between the TMI and the geological map. So in a situation whereby you are trying to have a grasp of the geological setting of the environment, despite the fact that the geological maps at the surface can give you good information, the TMI also can also give you an idea. And then the TMI data, which is magnetic data in this case, it's I believe it's much more accurate because it's going to tell you the exact boundary between those geology. I remember when we were doing our independent mapping, I think Tosin, we were in that same team together at Odiomu after we did our geological mapping. And then for about a week, we had to carry out some geophysical studies to know the exact boundary between those different geologies. We were seeing an outcrop somewhere, and then we were seeing another outcrop somewhere. We could not see the exact boundary between the two of them. So what the geologist is going to do for you is to just give you an inferred boundary. It doesn't have to. It doesn't mean it's the exact one. You just infer it and then they present it to you. But with geophysics, you can be able to have an idea of the exact position where the boundary between those two mythologies, where they really are. All right, so understanding and handling magnetic data acquired within Nigeria, it requires you to be able to understand some particular information about the data sets before you start before you proceed into interpretation, because understanding all those key elements is going to help you to have a good interpretation. Now, first on the list is the coordinate projection of the data. As we know, we have several types of projections. We have the UTM, we have the geographic coordinate system. It can be in geographic, it can be in projected generally. But even with the UTM, the datum can also be different. You can be working with WGS84. Sometimes the surveyors in Nigeria, they like working with the MINA datum. So depending on your preference, you can choose the one that you want. But any data that you are collecting, especially for those who are buying the aeromagnetic data from Nigerian Geological Survey Agency, it's important for them to understand each of this information so that they'll be able to make a proper decision. Like the magnetic data from Nigerian Geological Survey Agency, the projection is zone 32 north. Actually, there are some of the data sets that enters into the zone 31, and there's some that enters into the zone 33. But when you are working with a regional data sets, when you are trying to combine multiple data sets into one, you cannot be using varying projections on the same data. You need to just work with the consensus if you are planning to combine all of them together. So for those entering into zone 31 and those stretching into zone 33, you just convert them using zone 32. But the problem usually is for areas within zone 31, like Oyo State, some parts of Lagos State, when you display those data using projected coordinate system, you tend to see negative values there. I remember when I was doing my BSc thesis, my supervisor told me that my data was not credible. And the reason was because I was working with Lagos data. The data that I collected from NGSA was in zone 32 north. I just displayed it the way it was, and then I was seeing negative coordinates. So I didn't have a good understanding of projection back then. And then I was worried too at some point that how could I be getting a negative? But I just had to present it that way, that, well, this is what I got from the agency. Except you are saying that the data that the agency got was wrong. It was later on I now got to understand that Lagos falls within zone 31, and the projection should have actually been zone 31. So until I had to convert it, the negative values, they were still appearing. So when I converted it using zone 31, then everything was looking okay. So understanding this projection also can help to give you a good grasp of your interpretation. Then also the flight height of your survey. If you are having the sensor close to the source of your magnetization, you would expect that it's going to give you a higher intensity. Just like when you have two magnetic bodies and then you move them close to each other. As they are getting close, they will tend to attract because the force of attraction between the two of them is increasing. But as you are moving them away from each other, the force of attraction is still there, but it is no longer strong enough. So if you are having a survey with every other parameters equal, but the flight height is say 50 meters, and then you have another one with every other parameters equal to the first one, but then the flight height is 100 meters, then you will be seeing different images. They are going to be similar, but their resolution in terms of the information that they are going to acquire for you is going to be a little bit different. So when you understand the variations in this flight height, is also going to help to contribute, so that in the case whereby you are seeing an anomaly that is having low intensity, but then you recall that the flight height is a bit high, it may not necessarily be that the intensity is low, it may be because the flight height is a bit high, so that's why the intensity is sort of low. So each of these information, when you piece them together, it helps you to stay on course with your interpretation. And then also for your profile spacing, the whole magnetic data for Nigeria, the profile spacing is 500 meters. And then the one that was recently acquired and sponsored by the World Bank, the profile spacing is 150 meters. Their flight height is also different. For the first, as the whole one is 80 meters, and then for this recent one is 50 meters. So despite the fact that those two surveys, they are looking at the same place and they are going to give you similar information, they can never be the same, especially for anomalies that are smaller than 200 meters, for example. The 500 meter spacing may not be able to image it very well, but 150 meter spacing should be able to capture it appreciably. And then also your profile direction also plays a good role in your interpretation. Take for example, if you are having your anomaly trending in the north-south direction, and then you plan your flight survey and it's trending also north-south, you may likely miss the anomaly. Or even if you see the anomaly, you may be thinking it's profile induced. and then you do some micro leveling, and it's going to delete the anomaly. So when you are looking at those anomalies, when you are trying to plan a survey, your profile direction should be perpendicular to the direction of the strike of the anomaly you are looking at. And then the first speaker has spoken about this diurnal variations, the equator and the pole reduction, and also just for the sake of emphasis, whatever data that you are working with, these reductions, these data corrections, they are very important. They are like the basics of whatever you need to do before you start considering doing your filtering, like 1VD, 2VD, because everybody is always eager to do all of that. Do your residual, regional separations. All those things are not the first things that you do when you have a raw magnetic data. The first thing that you do is to correct for your diurnal variations. When you are done correcting for your diurnal variations, the next thing you do is to reduce it to either your pole or your equator. So just like the previous speaker rightly said, if you are working with a data set that is close to the equator, just like Nigeria is close to the magnetic equator, then you will be talking about reducing our data to the equator. There are some supervisors in the university that are always keen on having reduction to pole on their data sets. It's not I'm not against reduction to pole, but I feel it's not a must for you to have your reduction to pole, because at the end of the day, if you decide to reduce your data to the pole from a data that is acquired from a place like Nigeria, the level of distortion that is going to be introduced in your data set is going to be high. So at the end of the day, what most people do is they reduce their data to the equator and then they multiply it by -1, which is not also 100% correct, because if you look at the way I'm going to show you an image afterwards, so you are going to see the difference between a reduced to pole and a reduced to equator data set from a data that was collected from mid latitude. It's not exactly accurate. If you look at the image, I would like Mr. Tosin to bring up that image. If not now, maybe later on. The image where you are showing the models of those different bodies, where you have body A, body B, body C, you will discover that despite the fact that they are exactly opposite each other, you will see that their values are not exactly opposite, because the okay, let me out now. All right, go back. All right, beautiful. Now, if you see the place where this red line is, which in this case is reduced to equator, right? And then this green one being the reduced to pole, you see that they are not exactly mirror image of this other, mirror image of each other. If you look at the place where the line 0 is, you see that the line 0 is much closer to the green line compared to the red line towards the beginning of that profile. So despite the fact that they are giving you mirror images of each other, it's not exactly the same thing. But of course, because in magnetics generally we don't usually do quantitative analysis, it's usually qualitative analysis that we do. So if you just flip the reduced to pole and reduced to equator to get the reduced to pole, is equally fine also, because if you acquire data in Nigeria, for example, and then you subtract a base value, maybe like 33,000, because the values that you have for the TMI in Nigeria, that's the IGRF values basically, they are around 33,000 for Nigeria. So if you subtract a base value like 33,000 from the whole of your data, you are still going to be having the same image. The only difference is just that the values are going to be different. Now, when you are doing all of this analysis, when you are converting your TMI to RT, 1VD, and the likes, it's not much about the values that it is giving you. It's about the anomalies that you can see. And those anomalies are not really dependent on the intensity of those values. So it's not like if you're having some set of values ranging from 1 to 10, and then you're having another set of values ranging from 1 million to 1,000,010. It's not like they're going to be different. They are still exactly the same thing, because their ranges are still the same. Okay, so please back to my slide. All right, thank you. So like I said, if you also flip your reduction to equator, you multiply by -1 to get your reduced to pole. It's fine too. It can also work. But when you want to have your quantitative analysis, it may become problematic. But for the sake of qualitative analysis, then instead of you just reducing to the pole directly for a data that was acquired in Nigeria, you can just reduce to equator and then multiply by -1, and then you're good to go. All right. Other basic data cleaning processes, they include micro leveling. The error that usually occurs when you tend to flip the direction of your sensor. Take, for example, if you are acquiring a ground magnetic data and then you are going east-west. Let's say you move from your east to your west, and then you are going to the next profile, you are moving from your west to your east. It's not like you have to be dismantling your sensor every now and then and be turning the sensor. No, you just keep on working like that. So as you are flipping the sensor, it's introducing some minute error into your data set. So the process of reducing those errors is called micro leveling. So there are some data sets that it may not be very obvious in. So the micro leveling may not really be necessary, but there are some data sets that you see the obvious introduction of that error there, and then you need to find a way to remove them, either by using directional cosine or whatever method that you have at hand to use to remove such. All right, so this is an example of two data sets from the same location, but then they have varying properties. So the one on the left is the data set for 500 meter spacing, and the one on the right is data set for 150 meter spacing. So if you look on the left side of the screen, you see that the resolution is not as good as the one on the right. Of course, regionally, they are giving you the same picture, where you are seeing some magnetic low towards the western part, trending towards the northern part, and then you are seeing something similar too on the right hand side. But then, if you look closely and then you look at the anomaly that is just at the top of that big blue anomaly that you are seeing, you see that there is another small blue one that is looking a bit widespread within the low resolution, but on the high resolution is actually showing that it's localized, like it's very, very small. And then if you also look at the northwestern side, where you are seeing some north-south trending anomalies that are looking arranged, like alternating positive and negative. And then you look at it's also a north-south trending one just by the side of that longer one. It's not looking well defined on this 500 meter spacing, but on the 150 meter spacing, it's looking bogus. It's looking very clear, like something is there. You can even mistake the one on this western side on the 500 meter spacing as probably a noise. Maybe it was just something that happened there and it's the noise. You might be tempted to delete it from your data set. But if you look at this 150 meter spacing, it's actually defining it very well, showing you that it's actually real. It's not just some random spots. So the difference between these two is basically the flight height and the profile spacing. The profile direction are the same for both of them. Profile direction is northwest southeast. The profile spacing for the one on the left has 500 meter spacing. So that means that if you're having anomalies around 300 meter with about 300 meter radius or 200 meter radius, that may not be able to image it very well. But for the one of this 150 meter spacing, if you have an anomaly of 300 meter radius, 200 meter radius, it will be able to capture it and define it well. So basically, the essence of it defining it well is it's going to have multiple sampling points on top of that anomaly, compared to you having that same size of anomaly in 500 meter interprofile spacing. And then also for the flight height for the 500 meter spacing is 80 meter terrain clearance, and then the one on the right side is 50 meter terrain clearance. So that's a difference of 30 meters. So as it is closer to the ground, there is more tendency that it's going to capture whatever localized anomaly is within that particular environment. But if it is far away from the floor, if it is far away from the ground, as at that 80 meters, which is for the 500 meter spacing. Of course, it may still capture it, but then the intensity may be very low, forcing you to think that it's just noise. All right, so we talked about the diurnal correction. This is a representation of a data set that was acquired at a particular position in Nigeria from around 9:23 a.m. to 1:14 p.m. So imagine staying at a particular position and then acquiring continuous magnetic data reading. So you'd expect that if there are no variations, you'll be having the same value. Like every now and then that you just keep on acquiring data, you'll be having exactly the same value. But we can see here that that is not the situation. The value keeps changing. It's not changing suddenly, it's changing little by little, by little, by little. So that variation is what we need to monitor, and then we need to use this variation that we acquired here to correct for our magnetic data. So the way we usually do it is we have two magnetometers. One magnetometer is going to be stationed permanently at the base station, and then the other magnetometer is going to be the one that the person who is acquiring the data will mount on the body and keep on moving. All right. So the base station needs to be set up before we start acquiring our rover information. And when we are done acquiring the rover information, we need to stop that one first before we now pack up our base station, so that there's going to be data sets encompassing the old period of data acquisition. Right. So when we have that data, it's going to give you an idea of how the magnetic field has been varying over time. So with this information, we can now use it to correct our rover data. So basically, just like I said, this is how the diurnal data looks like. At the spot, just keeps on varying and varying over time. So you cannot really say that at this particular time, I have I'm going to have my data being linear, or I'm going to have it non-linear. If you look at these data sets, for example, now, if we look at what is happening almost towards the middle, we can see that there was a particular period where the value just kept on dropping, almost like almost at a linear scale, and it dropped for about 20 nanotesla. Oh, sorry, about 10 nanotesla. Each division is 5 nanotesla. Yeah, so it drops for about 10 nanotesla on a continuous basis, and it's looking linear. But if you look towards the beginning of the diurnal plot of the base station plot, you see that there's a place where you're having this sharp inflection, which is, if you look at that, the time frame for that is almost similar to the time frame where you are having this linear variation from this top to the bottom. So basically, you cannot really say that at a particular time I'm going to have this linear variation, at a particular time I'm going to have this inflection. Because if you plot the base station data for another day, it will be completely different from what you have here, but you still see the variation. So which is why it is important to always have that base station information in correcting your long-range data. Or at best, if you don't have two magnetometers, if it's just one you have, you can use the gravity method, where you are going to establish a base station, and then you take your reading for about 30 minutes to 45 minutes, and then you come back to that base station, you occupy, and then you continue again, and then you come back about another 45 minutes again, and then you occupy. But that's a very stressful method. Imagine if you need to cover a kilometer line of maybe 20 something in a day. You can achieve that using the rover method, where you don't have to be occupying your base station. But if it's just one magnetometer that you have, then before you even cover maybe 10 kilometers or 5 kilometers, maybe spending close to 3 or 4 days to achieve that. So depending on your budget, there are places where magnetometers can be rented if you don't have access to one of your own. All right. So as I was saying the other time, for the TMI, the RT If you are close to the equator, you reduce to the equator. If you are close to the pole, you reduce to the pole. Now, here's a schematic of is basically theoretical. What it looks like when you acquire data at the equator, when you acquire that same data, that same geological scenario at the pole, and then that same geological scenario close to the mid latitude, right? So at the equator, that's the first diagram to the left. You are seeing that you are seeing a negative anomaly. Anomaly is basically negative. But then at the pole, which is towards the extreme right, you are seeing a positive anomaly. Now at the mid latitude, you are not seeing you are seeing both positive and negative peaks here anyways. But you cannot really say that the positive peak is directly on top of the body, or the negative peak is directly on top of the body. So it is because of this scenario that we need to reduce to either the equator or the pole, so that we can directly place our anomaly below either the peak or the trough, as the case may be. All right, so this is the two diagrams behind this illustration are the TMI and the RT of the same area. They are looking very similar. It's a total magnetic intensity data from within Nigeria, and then we reduce it to the equator, and then we are having something very similar. However, if we zoom into it, if we zoom in a particular portion, you can see that despite the fact that they are similar, they are not exactly the same thing. Can see those little variations. Now those variations that are looking little here, if you actually look at them on the ground scale, they may be running to lengths of close to 2 kilometers, 3 kilometers. Now if you are using this for the purpose of mineral exploration, not just to have an idea of your regional geology. If it's for mineral exploration where it is targeted, you are trying to look for exactly where you need to, concentrate your effort, or probably where you need to drill. In most cases, you need to make sure that your data is as precise as possible. So you cannot just rely on only your TMI and then say because your TMI is close to Nigeria, you can just use like that. No, you need to be very, very specific. But if it's just for regional studies and you just want to have an idea of what is going on regional level, of course, you can decide not to use your RT, just work with the TMI directly, and then do your derivatives, and then you're good to go. Right? But when it comes to targeted explorations, usually for mineral explorations, those corrections, they are very, very important. All right, so when you want to interpret magnetic data for solid minerals, what are the things that needs to be considered? But like I mentioned earlier, it's not every project that requires magnetic data interpretation. For some, magnetic data interpretation is not useful at all. So you need to first understand the factors that come into play before you make a decision whether magnetic data interpretation is for you or not. So the first thing you need to understand is the geological terrain. Are you working with the sedimentary terrain? Are you working in the crystalline environment? Based on the answer to that, you can start thinking that will magnetic data be useful for me. Take for example, if you are working in a sedimentary terrain, you may not really see much magnetic variations because you're having a thick pile of sediment that are basically non-responsive to magnetism, and then they are overlying some crystalline terrains, which is deeply seated in kilometers, and then if you fly across or walk across such an area, at the end of the day, you'll just be seeing some sort of flat signatures because your sensor is very far away from where those deep-seated crystalline rocks are. So basically, the information that you'll be gathering is just regional information. You are not having any localized variations around that place because it's a sedimentary terrain. So if you're trying to study are those localized variation, and it's just a sedimentary terrain where you don't have any intrusives, where you are probably not having any sedimentary rock that has magnetic properties in it, like oolitic sandstones, for example. Probably you are just working in an environment that is just basically sandstone that has feldspars and quartz in it, and that's all. Then geological magnetic data may not be a good answer to that. But if you're working in a crystalline environment, maybe you want to find out the boundary between your granitic rocks and probably your schists. You can use magnetic data to delineate such kind of boundary. And another thing is there a magnetic property contrast? Because there has to be a magnetic property contrast before you say you want to use magnetic data. For any geophysical method, there is usually a physical property contrast that is in play. In the case of magnetic data, it's basically the magnetic property contrast. So if you are having a terrain where there is no difference in the magnetic property contrast, despite the fact that there are different lithologies, as long as their magnetic properties are similar also, it may not give you any information. But if you are having a geology that is having a particular magnetic magnetization direction, maybe another geology is having another direction, and then maybe geology having a different intensity, then magnetic data interpretation could prove useful in such a kind of terrain. And then another question that you need to answer is it a direct or an indirect approach? Now, what I mean by that is, for some mineralizations, magnetic data may be used as a direct method to get exactly where those mineralizations are. Take, for example, if you are exploring for iron ore that is rich in magnetite, then magnetic data interpretation could be a direct method in that case. Take, for example, if you're exploring for if you are exploring for oolitic sandstone within areas like Cotton Karfi in Kogi State and all, you can use magnetic data to delineate exactly where those bodies are. You can even use it to delineate the boundaries, the extent, and all of that. But if you are looking for a mineralization like gold, or probably a mineralization like lead or zinc, magnetic data will still be helpful, but it's not a direct method. It will be helpful in such a way that if your gold is structurally controlled, like you have the gold around places within Zamfara State, where you see them in all these quartz veins, then you can use magnetic data to delineate such an area. So basically what it's going to do for you is magnetic data is going to help you to locate where those structural features are, where you're having all those quartz veins and the likes. As long as they are thick enough, it will help you to delineate them. However, it does not mean that all the quartz veins are mineralized. So there has to be some sort of follow-up method that you use to complement that. Well, by and large, the point here is that not all mineralizations can be mapped out directly using magnetic method. There are some that at best they are just going to be an indirect method for you to like reduce the zone of search. Maybe if you have a very large area like 200 cadastral units, maybe 40 square kilometer, for example, you may not have the manpower to go around all that 40 square kilometer. You want to just concentrate on a particular area. So using magnetic data as the regional magnetic data, you can have an idea of the areas where you have to concentrate your efforts. So instead of having to go through the whole 200 cadastral unit, you may restrict your work to just about 15 to 20 cadastral unit, and then deploy people to go to the field to check out exactly what is going on ground. That way you have already reduced your search area instead of just launching into the field and start moving about like the artisans they do. All right, so another question you need to ask is the occurrence of this mineralization. Is it favorable for delineating such mineralization? So we mentioned the other time that you can use magnetic data to explore for gold. Now, if you consider the gold occurrence in places like Elisha, most of the gold that has been won around that axis are alluvial. And then depending on the person who is actually trying to mine, there are some that are not interested in anything primary. They prefer to just work with alluvial recovery and they are good to go. So if you start telling them about some gold being inside some veins, they are not really interested because they might be considering that the process of getting the veins, crushing it, and all of that. So they just want to do their washing and then they are good to go. So for those who are restricting their exploration to just uh, the alluvial deposits of gold, in that case, magnetic data is not going to do anything for you. Because remember that the magnetic data itself is not sensitive to the gold per se. It's an indirect method in the sense that most of the time those primary gold are usually associated with sulfide minerals. So those sulfide minerals also, they have a way of aligning together with all these quartz veins. They are usually within those quartz veins, and those quartz veins, they have some sort of alignment. So when you acquire your magnetic data, what is being displayed for you really is the variation between that quartz vein and the host. Now the quartz vein may not be mineralized and it may be mineralized, which is why that follow-up method is required. So you can see how magnetic data comes into play. When you interpret your magnetic data and then you are seeing all those lineaments, not all those lineaments are mineralized. Some of them are mineralized, some of them are barren. So when you have been able to delineate all those locations where you're having all those your quartz veins or your suspected quartz veins in this case, you can now do some sort of follow-up studies on them, probably go to the field, break samples, or if you cannot see them at the surface, you can use some other geophysical methods to understand what is happening at the subsurface. So, like I said, if you are working with alluvial gold, for example, magnetic data is not going to do anything for you because your magnetic data is not sensitive to your gold itself. It is sensitive to the host of that gold. Okay, so for alluvial mineralization of gold, magnetic data is not going to really do anything for you. Or probably if you are looking for lithium, which is the in thing in Nigeria now, if you are looking for lithium, using magnetic data may not really be a good method for you because the magnetic data is not going to tell you whether the pegmatite vein that you are working with is mineralized or not. Now, most of the time, these pegmatite veins that we're even talking about, they usually blend together with the geology of their host rock. So magnetic data may not even be a good method to delineate the boundaries between those pegmatite veins themselves and then the host rock. So at the end of the day, instead of considering a geophysical method, you may be looking at geochemical methods, like going to the field, picking samples, analyzing them in the lab. You know. So the next thing we also need to consider is the estimated size of the mineralization and or the mineralization host, depending on the case, relative to the resolution of the available magnetic data. So just like I've mentioned multiple times before, that if your anomaly is just about 200 meters in diameter, and then you are having a data set of 500 meter spacing, you don't expect the data set of 500 meter spacing to give you a good picture of a 200-meter anomaly. But if you are having a 150-meter spacing data, and then your anomaly is about 300 meters diameter, then you'd expect that 150-meter spacing data should be able to resolve that kind of anomaly very well. So those are the questions that you need to ask yourself. Are the veins that you are targeting on the field, are they thin? Are they wide? If they are wide, how wide are they? Are they long? Are they elongated? If they are elongated, how elongated are they? So that you will not just you not just analyze only your aeromagnetic data and then you feel that is where it stops. Sometimes you may need to do another magnetic survey, but this time around you will reduce the profile spacing. So instead of doing a 150-meter spacing that you had before, you may need to go to the field and do 50-meter spacing to be able to properly resolve what is happening locally within that environment. All right. So just like you said, we don't usually stop there because in most cases, magnetic data is like a reconnaissance method. It's one of those methods that before you start doing any exploration on your site, just get magnetic data, analyze it, and let us see what we have regionally, what we have structurally around that environment. So basically, when we have that when we are done with that and then we've gone to the field to acquire some geological data and all of that, we usually have to come back and then, add another method to it so that we may be able to confirm whatever theory that we have been able to postulate from our magnetic data and our geological data that we have gathered on that particular site. So take for example, if you are exploring for lead within Benue Trough, which is actually within a sedimentary terrain, you would expect that around the host rock, everywhere is going to be sort of magnetically quiet. And then where you are having those veins, whether they are hosting lead or not, you start seeing those sharp lineaments. And then if you use some enhancement methods like your 1VD, which the next speaker is going to be talking about, as your 1VD, your 2VD, and the likes, it brings it out very well. And then you can be able to see exactly where they are, plan another survey across them. So one of the surveys that you can use, okay, before we start talking about the surveys, we also need to consider the property for this particular mineral that we are trying to explore. One of the properties that we can consider is resistivity, another is chargeability, another is density, and then sometimes the elastic properties. So in the case of gold, one of the properties that we usually consider in most cases for gold is the chargeability. Chargeability basically is okay. Let me take our mind back to when we were still little children. When we were in primary school, there is this play that we normally used to do. We carry a pen, we would rub our head with that pen, and then we take a small piece of paper, we cut, and then we use that pen to pick up that paper, and then it picks it up. Everybody is happy, excited, and all of that. But over time, that pen is not be able to pick up that paper anymore. So that's basically the principle of chargeability. You send charges into the ground, and then it charges up the ground, and then you suddenly remove the charge. So by the time you remove the charge, you will now monitor the rate at which the bodies that were charged, the rate at which they are decaying. So you would expect that if I charge up a body like the sulfide, and then I charge up a body like quartz, you'd expect that the sulfide is going to retain more charges over time compared to the quartz. So the moment I remove my current that I'm using to charge up the ground, the moment I turn it off, the quartz is going to dissipate the charges faster compared to the sulfide. So in that case, we can categorically say that the sulfide, it has higher chargeability compared to quartz. All right. So that's basically the principle of chargeability. So depending on the mineral that you are looking for, chargeability can be a good factor to consider in choosing the next method to use to follow up your magnetic data interpretation. And for chargeability, we are talking about the induced polarization, just like the word says, induced. So you induce the polarization and then you remove it, and then suddenly you start seeing everything decaying. And so based on the rate of decay, you have an idea of which one is chargeable and which one is not chargeable. And then another property is resistivity. How resistive is the body that we're looking for? Another property is the density. I think for density, we basically make use of the gravity method. Chargeability, high P. For resistivity, we use electrical resistivity method. And then for elastic properties, in most cases, we make use of the seismic refraction. Seismic reflection is usually for deep-seated mineralization. That's for oil and gas. But if you are just working with near-surface anomalies, restricting your work to near-surface geophysics, then maybe restricting yourself to just the seismic refraction. And then also another thing to consider is the estimated depth and size of the target anomaly. If the anomaly, if it is deep-seated and you want to have a good 3D image of it after acquiring your data, there are some methods that they penetrate deeper and then they still maintain a high resolution. But there are some that their resolution is just basically at near surface. Take for example, if you are trying to do your 2D pseudo section, you can consider a method like WENA or a method like dipole for your 2D resistivity pseudo section. Now both of them are going to give you 2D pseudo section, but the resolution that dipole is going to give you is much better than the resolution that the Werner is going to give you. So Werner is going to penetrate deeper, but the resolution is not as good as the resolution of dipole. However, dipole does not penetrate as deep as Werner. So those are the things that you need to consider. The mineralization that you are looking for, is it very close to the surface or is it deep seated? If it is deep seated, then you may be considering a technique like Werner instead of favoring dipole over it. All right. Before I start answering any of these questions, let me just quickly finish this presentation. So, in conclusion, by understanding the principles and challenges of magnetic data interpretation, any mineral explorationist can effectively utilize magnetic surveys to identify potential solid mineral deposits and then advance the exploration programs. Now, the basic principle of any exploration is that you want to narrow down your area of search. Let's say you are looking at a space like Nigeria in a whole, and then you acquire your geological data, your geological information, your magnetic data, your radiometric data, and everything. After analysis, you can now narrow down that, oh, I'm only interested in gold, and the gold that I'm interested in, I want it for Osun State. And then you go further, and then you narrow down. You take the information that are available for Osun State, and then you look at them, and then you say, oh, I'm not interested in the whole of Osun State. I'm only interested in the regions around Ifewara and Elisha. And then you go further, you gather all the information that you can lay your hands on regarding those locations, and then you keep on narrowing down till you get to a particular area where you can lay your hands on and say, oh, I can concentrate on this particular area. That is basically what any exploration program does for you. So if you are not working with a place as large as Nigeria, if you are working with, let's even say, a 2 kilometer by 2 kilometer land, you don't want to work on the 2 kilometer by 2 kilometer land. You want to be able to narrow down that this is where I'm going to start my excavation from, or this is where I'm going to start my drilling from, or this is going to be where I'm going to start my pitting from. All right. So your exploration program should be able to give you a pointer towards that decision that you want to make. All right. So, like I said, magnetic data is basically a reconnaissance method that gives you like an overview of everything. It gives you an overview of everything, So when you have that overview, you can now begin to narrow down from there. So for the sake of those who are not aware, on the website of Nigerian Geological Survey Agency, we have all the newly acquired airborne magnetic and radiometric data. It has been divided into sheets. So when you go to this website, you would see there it has been divided into sheets. The extent where the new data set covers, you see there. So anywhere that you are interested, you can just click on it, and then you download the zip file. So the zip file contains your magnetic data, it contains your radiometric data, and the radiometric data being the potassium, the thorium, and the uranium. So the ratio for the three of them can give you an idea of what is going on at the surface, basically for regolith mapping. All right, so thank you so much for your time. But before I go, I'm seeing some questions popping up here. Mr. Tosin, are you there? Reading, is there really any need to reduce Nigeria data to the pole? I think reduction to equator is suitable for Nigeria. Yes, this is correct. I think that's what I said earlier. You don't really need to reduce to the pole if you are working with Nigerian data. But it's just that most of the time when researchers are working with Nigerian data, before they start their work, they take journals from the US. They take journals from Australia. Those regions, they are closer to the pole than the equator. So you'd expect that their own data, they reduce it to the pool. So because you are trying to model your own research after the research of someone else around that region, you see some supervisors, they start mounting pressures on their students that they must reduce their data to the pool. They should just follow the format of this particular professor, or they should follow the format of this particular scholar. It's not always so. Understanding the data is going to help you to know whether what you are even trying to do is useful or not. So instead of, just like rightly said, instead of reducing it to the pool, just stick with the reduction to the equator. But of course, you also need to pay attention to the fact that the way you interpret data that is closer to the equator is almost opposite the way you interpret data that is closer to the pole. So in a place where you are seeing low magnetic intensity on the Nigerian data, for example, that place actually means that the magnetic intensity is high. So it's that confusion that some people sometimes try to avoid. Why they just multiply by -1 and reduce it to pole, and then they just interpret it that way, so that at some point they're not going to, mix it up. But I just feel that if you reduce to the equator and then you understand that this opposite, it should not be a problem. But if you feel comfortable flipping it, multiplying it by -1 and then changing the direction of the anomaly, then that's fine too. But the most important thing is when you are doing your interpretation, it's important for you to let us know the procedures that your data has gone through, so that when I'm seeing your data, I can be able to understand the different level of processes it has undergone. If you show me a 1VD map now, you should tell me whether the 1VD was derived from your RTE or your RTP. Because if the 1VD was derived from RTE and it was derived from RTP, both of them, they are opposite each other also. So I'm not supposed to be interpreting your 1VD from RTE the same way I'm going to be interpreting your 1VD from RTP. So those different levels of processing, they need to be specified so that it will reduce the level of confusion from the standpoint of whoever wants to, the third party wants to understand your data. All right. So I think that will be all for now. Mr. Tosin, uh, thank you so much for this opportunity. Over to you now, please. Okay. I think there is some network issues somewhere. So pending the time that that issue is fixed, I'm seeing some other questions here. Uh, are you saying that the new aeromagnetic data is free? Oh yes, it is completely free. You can just go to the website and download. Right. You can go to the website and download it. Just click on whatever sheet you are interested in. As long as it's captured as part of the ones that are free, then you can go ahead from from the NGS's website. I can assure you of that. And it's not only magnetic data that are free. If you browse through the website, you also see some geochemical data also for some particular area. It's not for the whole of Nigeria, though, just for some specified area within Nigeria. All right. Welcome, Dr. Anson. I can't seem to lay my hands on Mr. Tosin.
All right,
I
thank you
think he's having
for
some.
having me. Yeah, can you all hear me? Good
Yeah,
afternoon.
I can hear you.
Yeah, all right.
Basically, I'm the
So,
only one who can respond to you speaking. Every other person is just talking on LinkedIn. So please go ahead. You are live.
okay, I'm still waiting for my PowerPoint to be uploaded anyway. Uh, Shared it already.
Okay, Mr. Tosin, welcome back.
Yeah, Mr. Tomoa, thanks so much
Looks
for
like you
that
traveled out.
wonderful presentation. I was actually working behind the scene to ensure that things go as we expect. Because as it is now, we are really running behind schedule. This almost this almost 3:40, and we are meant to end this webinar by 4 as much as possible. Uh, Because I understand that there's a glitch in the network at some time, and then we also need to attend to questions that people are sending to on LinkedIn. So, Dr. Ayodeji Asenayola, we are still waiting for you to upload your PowerPoint slide so that we can present it to LinkedIn.
Okay, so I will re-upload them now. I sent them earlier. So I think I uploaded them again. If you can see them.
Yeah, I can see it now. So we have it on the screen right now.
Okay. So let's get right to it because of our time. Good afternoon, everyone. So we've been hearing about the interpretation of magnetic data. We have heard about the global perspective and the Nigerian perspective. It's been very enlightening. Yeah, I've learned one or two things myself. My own assignment here this afternoon is to talk about the challenges of magnetic data interpretation. As you may observe as we go on, some of the issues that I'll be touching on have already been talked about at length. I think that makes our work a lot easier here. So let's get right into it. So interpretation, if you're familiar with geophysics, is the last stage of the geophysical endeavor. Geophysics generally proceeds in three stages. We have the acquisition stage, the processing, and then the interpretation stage. So again, interpretation is the last phase of any geophysical endeavor. It is very essential to mention here that the setup the acquisition, the way acquisition is set up is quite important if we are going to have successful interpretation, and then the processing techniques that we choose or that we work with also have a lot to do with what we can be able to achieve during the stage of interpretation. It's always important that one works with the objectives in mind when carrying out, when setting up the acquisition, and then when applying processing techniques. Uh, so typically, processed and enhanced data can be interpreted both qualitatively and quantitatively. Qualitative interpretation speaks to the observation of features, okay, as it relates to the geology of an area when one is looking at a magnetic data. And when we are talking about quantitative interpretation, we are usually referring to modeling, all right, so this is more tilted towards the quantitative side of things. So results in when it comes to magnetic method are generally presented as profiles, maps, and models. So problems that might be associated with the interpretation of magnetic data are albeit solvable. They include non-uniqueness, the dipolar nature, which has been spoken about at length, remanence, superposition, the depth at which the data, or I mean the depth of magnetic source, say for example, or the flying height or the height of elevation when we are dealing with airplane, and then the availability of constraining data. I must state here that, or emphasize here, that all of these problems are solvable. In fact, this is why our magnetic method still comes in, and it still comes in very useful, because even though these problems exist, they are all very solvable problems. So down to the problem of non-uniqueness. And non-uniqueness is a problem that cuts across geophysical methods generally. But for the potential methods, including your gravity and magnetic method, the problem of non-uniqueness seems to be pronounced. So yeah. So what does non-uniqueness mean? As many of us might know, it means that when a particular anomaly is it's similar, when we're dealing with two different subsurface situations, and yet you are generating similar anomalies. You say you are dealing with the problem of non-uniqueness. That is, the character of the anomaly is not unique to a given situation. So this problem is a problem that is common to both to the potential field methods generally, and the magnetic method of course is not left out. If you look at the example presented here in the schematic, you could see that we're dealing with a fault and an anticline, and yet the anomaly responses of both subsurface structures are clearly the same. So one of the problems, as one of the earlier speakers or the earlier speakers alluded to, one of the methods of solving this problem is by applying geophysics in combination. That is, you do not use geophysical methods in isolation. Sometimes you add other geophysical methods for a better understanding of what is going on within the subsurface. The next problem or the next challenge that I want to talk about is something that has been very well spoken about today. Of course, it's the dipolar nature of magnetic fields. As it's been said, magnetic fields are generated from the core of the Earth, essentially the outer core of the Earth. As you may be aware, the outer core of the Earth is either semi-solid or a liquid, and so there are convection currents going on in the outer core of the Earth, and as a result, a field is generated, and that field causes the Earth to behave like a giant magnet. Also, as it's been said to us, the field generated at the outer core of the Earth is approximatable into a dipolar feature, and that and then the crustal materials, okay, which from which magnetic readings are taken, imitate what is actually going on within the core. And so as a result, the dipolar nature of the core fields is always reflected when we take measurements. However, the position you are at on the earth determines how this dipolar nature will affect your reading. Say, for example, you are located at the pole of the earth. The type of anomaly you get will be a body-centered positive anomaly, because the inclination at this position is at 90 degree. And so you are some things have already been said about the reduction to pole filter. So reduction at this kind of position of the earth, that is at the pole, a reduction to pole will not be necessary, all right, because this is when we reduce to pole, which some people actually refer to as rotation to pole. We're trying to achieve the same situation that occurs at the pole when magnetic readings are taken elsewhere. So that's why we try to mathematically translate this reading to the pole, which is essential. So because what we have at the pole is like a monopolar reading, and it makes our interpretation a lot easier. However, if one is located at the equator, what you also have is a body-centered negative anomaly. But if you are somewhere in between the pole and the equator, you would see that the dipolar nature of the Earth's magnetic field generated at the core will be reflected. If you look at the schematic, you can see that is very, very well demonstrated. In the schematic there, the magnetic anomalies that we can see and the field, you can see the field generated around them. They are it's for the same object, but at different positions around the Earth, and you can see that there's a variation in the anomalies. To add to what has already been said about the necessity for carrying out the RTP or to applying the RTP filter. Yes, if you're located somewhere around Nigeria, it's actually advisable to use the reduction to equator filter, all right, because reduction to pole, if applied around the place, to data collected around somewhere like Nigeria, not a lot of noise will be introduced into that data. A lot of noise will be introduced. However, it is also pertinent to state that certain practitioners they prefer not to make use of the reduction to equator filter because of the fact that some things are hidden. So they use another filter known as reduction to pole at low latitude, RTPLL. So if that is very well used, you might still get a very good, the problem of that dipolar nature will still be very well solved if one can apply it appropriately. So moving on to the next point, one of the other challenges that one might have while interpreting the magnetic is the problem of superposition. So this is just about understanding the magnetic data, really. What this suggests is that when you take a magnetic reading at a point, what you have is a combination of many sources. This is the way potential fields generally behave. So you have, when you collect the data at a point, what you are dealing with is a combination or a sum of several sources. So there is usually always an interference of sources. It may then become difficult to be able to tell one body apart from the other. Long wavelength anomalies from deep sources might obscure locally important smaller wavelength abnormalities. A separation of regional magnetic trend must be done. Essentially, this is why we always carry out the regional residual separation, which is a usual practice when one is processing the magnetic data. So this is why one of the reasons why we carry it out, because of the nature of magnetic data to be a combination of many magnetic sources. Further, drilling information can supports the existence and location of distinct bodies. In the example that is presented here, this example is from somewhere in northern Tasmania. We can see stacked total magnetic intensity profiles. What we can see there, you can see that we have broad anomalies to the, if you look at the profiles towards the top, presented in this example, you will see that you have broad anomalies around the top area. So the broad anomaly is due to Proterozoic metasedimentary rock at a depth of 1 to 2 kilometer. If you now go to the bottom, towards the bottom part of these profiles, you see that there is a small anomaly. There are smaller anomaly signals. These ones, they are responses to superficial basalt flows, which are about 100 meter below the magnetometer. So, this is a very clear picture of how superposition occurs in our magnetic data. Another issue, and this I must say has already been talked about, is the depth of the magnetic source or the magnetometer elevation. So it is a fact that depending on where the magnetic source is located in the subsurface, depending on its distance away from us, this would affect the strength or the intensity of the magnetic anomaly that we can obtain from it. So depth of a magnetic source of interest is a factor to determine whether it will be successfully interpreted or not. This effect is even more pronounced if data collection is done from an aircraft, which is some distance away from the surface. If you look at the example in the diagram, you could see that if you look closely, you will see that for the signals, for the anomaly, the profile there that was taken at 10,000 feet above the ground, there is practically no anomaly revealed. There's practically, it's essentially a flat line. It's essentially a flat line. And then at 4,000 feet above the ground, we can see that we have some anomaly. You can see that there is a shoulder there, you can see that something is actually going on. But 1,000 feet above the ground, which is the closest, okay, which is the closest to the ground, this is of course from an airplane survey, you could see that the anomaly is very, very well defined. So depth, of course, plays an important role when magnetic data are collected, or when we're trying to interpret magnetic data. All right, going on, mega remanence has also been spoken about. So of course we know that the operative physical property for the magnetic method is not just susceptibility. Remanence is also sometimes involved. Remanence has already been spoken to, in that it's the magnetic property that is trapped within a body, a crustal body, perhaps from a prehistoric event. All right. So yeah, so that's remanence for you. So one has to pay attention to remanence as well. In magnetic surveying, susceptibility isn't always the only factor responsible for the field generated, by a source. Remanence, which is an inherent property of some rocks, is sometimes involved. The direction of polarization of the rocks is usually assumed to correlate with that of the induced field from the car. However, when remanence is involved, it makes interpretation more complicated, because as a matter of fact, it might actually not be the same as the direction of the trend of the susceptibility. So remanence sometimes makes interpretation quite complicated. If, for example, if one is trying to note the direction of trend of a whole body within the subsurface, okay, if the appropriate information about remanence is not known, one might not be able to successfully deduce that. And so remanence is usually an issue. And lastly, talking about the challenges or the problems that one can encounter in magnetic data interpretation is the constraining data availability. Constraining data availability. Constraining data is part of what we use to solve the problem of non-uniqueness. Constraining data could include things like as simple as geologic information. It could be things as it could be talking about the rock properties. Okay, perhaps laboratory measurements of rock susceptibility. Say, for example, which when one wants to do modeling, are quite essential information to take care of the problem of non-uniqueness. But in reality, this information is not always available. Perhaps maybe for the lack of funds, or perhaps for the just for the fact that some of these sources of interest are far removed from the surface, and so it becomes quite difficult to access this constraining data information. It's usually a huge problem where modeling is concerned, when one wants to be closer to accurate results. It is a challenge, but it's also solvable. And then before I close, I want to also show a simple example of this, the magnetic anomaly presented in this frame is from somewhere in Osogbo. It's from an area in Osogbo, and in the first frame, you could see that we had not applied the reduction to equator filter. Here is what we are seeing here is how we can take care of the dipolar the effect of the dipolar nature, okay, by using the reduction to equator filter. So in this, in the first frame, what is easily noticeable are the pairs, the dipolar nature of the field reflected in negative and positive anomaly pairs. So if you look closely, of course, the brown coloration suggests that we have negative anomalies or low anomalies. So you can see that we have the blues are the highs. So the anomalies are paired across the entire study area. You can see a pairing of negative and positive anomalies. This makes this interpretation at this stage quite cumbersome. Of course, the inclination around Osogbo here is about 13 degrees. So you can see the dipolar nature here is going to affect the interpretation of this. And then you can now see in the reduction to equator, in the application of the reduction to equator to the anomaly, you can see that the anomalies are now very well defined. They are very well defined. Actually, it mimics the geology of the study area very, very, very well. So we see the importance of applying the necessary filters to get the best results out of our magnetic data interpretation. So I would like to conclude by saying that paying due attention to the various challenges that one may encounter in the magnetic data interpretation highlights the importance of the techniques that have been developed for dealing with these complications. So it gives us a great appreciation of why some of these filters have been put in place. Okay, so that's what the filters are for. So even though the challenges may be there, so the filters are there to take care of that problem. It's also important to reiterate that successful interpretation procedure of the magnetic data is dependent on proper acquisition, design, and effective data processing. So yes, one must always work with the objectives of the survey in mind, and this will go into how the data is even collected to begin with, what spacing one, the choice of spacing that one makes. Mr. Akombi said quite a number of things about this, about the dimensions of the magnetic source, that one must consider things like spacing. Okay, not just station spacing, also profile spacing. so that you can have you can be able to view very well uh, the objects of interest within the subsurface. So finally, successful identification and characterization of magnetic sources is possible when the necessary available solutions to these limitations are deployed. I want to thank you all very much for listening. I also want to thank the host, Mr. Tosin Oyeni, for the opportunity to be a part of this presentation. I want to use the opportunity to say a very happy birthday to you. Thank you all for listening.
Our time is fast spent, and at this juncture, we'll have to bring the webinar to a close. However, this is my conclusion of the whole webinar is that whatsoever you want to do in your magnetic interpretation, always understand that the nature of the Earth magnetic field, uh, your data acquisition parameters and also instrumentation and the procedures you adopt, the techniques you adopt for your data processing will have implication on your data interpretation. So that's what I have seen that is common from the first presentation to the second presentation and to the third presentation is that everything that from the nature of the Earth magnetic field to your data acquisition and to your data processing will definitely have effect on your magnetic data and the interpretation of your magnetic data, particularly what is obtainable from the interpretation of your magnetic data. Thank you so much for being part of this webinar this evening. There are a lot of questions that we have on LinkedIn. I'm sure we won't be able to really attend to the question. Mr. Tomiwa tried as much as possible to attend to some of them, but there are still questions that need to be attended to. Somebody was asking, please, how can we get the slides? For you to get the slides, we have to meet with, after the webinar, we have to meet with the speakers, and if they will seek their consent, maybe they are interested in releasing their slides to you or not. And for whoever asks that question, I also like to clarify is one of uh, a particular portion of the slides. And now the second question has been answered. Is there really any need to reduce Nigeria data to the pool? I think reduction to equator is suitable for Nigeria. As Mr. Tomiwa answered it, Nigeria is close to the magnetic equator, and the principle is that when you are close to the equator, you reduce to equator. When you are very close to the pole, you reduce to the pole. Caesar, are you saying that the neuromagnetic data is free? To the best of my knowledge, because I think Mr. Tonwa is the one that should be in the best position to answer this question, but to the best of my knowledge, the neuromagnetic data being acquired now, they are being sponsored by the World Bank, and the World Bank expect that this data should be made available to people free. However, not the whole of Nigeria have been fully covered by the new set of aeromagnetic data. So you will discover that for some certain areas that if in certain areas you want to work on, if let's assume you need like 4 sheets of aeromagnetic data, you might discover that just 2 have been acquired in the new set of aeromagnetic data, and their specification that was used to acquire them, the whole aeromagnetic data and the aeromagnetic data, they are completely different. So if you will need the whole 4 sheet, since the new aeromagnetic data for 2 of the 4 sheets are not available, you have to go for what? You have to go for the old set of aeromagnetic data. So because you can't match the new and the old together, there will always be a jump. There's what is called jump in magnetic data. There will always be a jump in the magnetic data, because if you acquire magnetic data at a particular place today and you apply uh, a set of correct data correction to it, and you come again tomorrow to acquire the same magnetic data there, and you apply the same set of exactly the same data reduction procedure, that with the same parameters that you used yesterday to it today, you will discover that you will have the same pattern of anomaly, but you will discover that not the same value. So there is what is called a jump. There will be a jump. So you trying to acquire data that are acquired, the magnetic set of aeromagnetic data that are acquired at different times, you will just discover that what there is no flow into the from the old into the new. There will always be a jump in the magnetic data, so they are not leveled to the same reference datum. To the same reference datum. Uh, it says, okay, is the neuromagnetic data now free, sir? Oh, so we cannot really fully say. There are some that, to the best of knowledge, they are free. They are free, and I've been able to obtain it for some persons for some certain work. But however, we can't fully say that all is free, except Mr. Tomiwa. I will later attend to that on LinkedIn. Another person has very good presentation. We hope to have your PowerPoint slides. As I said earlier, that will require that after the webinar, I seek the consent of the speakers, whether they are willing to release it or not. And thank you so much. And I want to believe that many of the some, not if not all, some of the figures you see in the presentations in the slide PowerPoint slides today, they must have been obtained from some sources. So, and for example, even my own PowerPoint slides, I discovered that I forgot to include this reference to the sources for certain figures. So I'm saying this so that we anonymously acknowledge every sources where we got the figures from, so that they won't be annoyed when they see it in our slides, in our presentation, that we did not reference them as the source. We are sorry about that. We forgot that it was an oversight. Please, if you are the owner of any of the figures we used and for, we did not acknowledge the source of it, please kindly bear with us. It was an oversight, and we are sorry about that. Thank you for this being part of this webinar. It's been a wonderful time and a wonderful experience. Dr. Ayodeji Asanayola, thank you for staying from the beginning to the end. We couldn't have the fourth speaker present. As I said earlier, he was unavoidably absent because of the demands of his program at his school. So please kindly bear with him. Maybe some other times we'll have him come to make presentation to us. It might not be on the enhancement techniques or for magnetic data interpretation. It might be something else in times to come. So till another time, one will be coming your way under this initiative, Magradel from Etosin Juice Consulting Limited, to be a channel of blessing and insight and education to you. Please do have a wonderful time and wonderful professional experience at your various on your various ends. Thank you once again. Till another time. Thank you. See you again next time.